Welcome again to my channel. Today, we will be talking about time value of money. Actually, this is just the part 1 on my discussion on the time value of money. In my opinion, accounting students should be able to master this topic so that they can understand a lot of higher accounting topics like notes receivable and notes payable, investment in bonds and bonds payable, and on capital budgeting topics like internal rate of return and many others. So I hope that my series to time value of money can help. My series of videos will be centered on 3 main topics. The first is the mastery of future value, the second, the present value, and the interpolation. We're going to tackle not just the concepts but also the calculations. This particular video is mainly discussing the topic future value, but it also includes other topics. Well, here's the list of the subtopics. Number 1, concept of time value of money and simple interest. Number 2 is the concept of compound financial interest and the future value. Number 3 is all about future value of 1. Number 4 is future value ordinary annuity. Number 5 is future value annuity due. And the bonus topic, which talks about multiple and equal investments. It is important to note that these topics includes illustrations and solutions. So this is again Let's Marby Ikasama, and let's start. So we are now on the first part entitled Time Value of Money and Simple Interest. So what is time value of money? The concept of the time value of money is that your 1 peso today will be worth more in the future because of interest. Actually, the simple interest is directly related to this one. So if you have a debt or an investment, those will grow because of interest. For example, you want to invest 1 million to earn 5%. How much will it be after 2 years and 6 months? To answer that, we need to get the future value of the investment, which is the principal plus interest. The principal in this case is the amount invested. The interest is computed as principal times rate times time. But I would like to emphasize that whenever you are given a rate just like this one, the 5%, please assume that it is an annual rate unless otherwise specified. So let's compute first the interest. The interest is 1 million, which is the principal, times the rate of 5% times time. So this time can also be expressed in fraction, where the numerator can be the number of months over 12 months or the number of days over 360 or 365 days. So again, 1 million times 0.05 times 2.5 years is 125,000. So in order to get the future value of the investment, we need to add the principal of 1 million plus the interest of 125,000. We have 1,125,000. So that's it for part 1. So we are now on the second part and the third part, which is entitled Compound Interest, Future Value, and Future Value of 1. So to start this, we need to compare first the simple interest versus the compound interest. So interest is considered simple when it is charged only to the principal. So how about compound interest? The compound interest is an interest not only charged to the principal but also on the interest accrued but still unpaid or uncollected yet. It might be clearer if we have an illustration. This illustration is coming from the previous example where you want to invest 1 million at a rate of 5%. The question is the same, which is how much will be your investment after 2 years and 6 months. However, there is a red colored text here which states that the interest is compounded semi-annually, which basically means the charging of interest is every 6 months. So applying the concept of compounding, we have a timeline for 5 periods. Why are we considering 5 periods, sir? It is because of this compounding mentioned in the problem. So now, each period that we have is only for 6 months, and each year has 2 periods. So 2 periods times 2.5 years, that is equivalent to 2 years and 6 months, the 2.5 years. So we have 5 periods. So let's go now to the computation. So you have 1 million now. And after 6 months, it will grow to 1025. Actually, the 1 million has been multiplied by 1.025 or 102.5%, where 100% is for the principal invested and 2.5% is the interest. So where did the 2.5% come from? It is from the 5%. But then again, this 5% pertains to annual rate, and we are just considering 6 months, so we're gonna use the 2.5%. So beware on the compounding schedules mentioned in the problem because it will affect the computation. So in the succeeding years, it will follow the same pattern. The 1,025,000 will be multiplied by 1.025 and it will become 1,050,625. But if we analyze this, the whole 1025 in this period, which is composed of the principal of 1 million and the interest of 25,000, has been subjected or has been charged with interest because, as you can see, the totality of this one has been multiplied by 1.025, in which this 1.025 is equivalent to 102.5%, which is already inclusive of interest. So that's the concept of compound interest. Let me remind you again that the compound interest is the interest charged not only on the principal but also on the unpaid or uncollected interest. So let's continue the timeline until we get the final answer. So the 1,050,625 times 1.025, you're gonna get 1,076,890.62. You multiply that again by 1.025, you're gonna get at the end of year 2 1,103,813, and on the last period or at the end of 2.5 years or 2 years and 6 months, your investment will be 1,131,408. Let's go now to the future value of 1. When answering the question how much will be the value of the investment after a specified period of time just like this one, you can answer it with a timeline just like this one. But if we are talking about long periods of time, let's say for example, instead of 2.5 years, we're gonna consider the 25 years, then it would be difficult to get the answer through timeline. Because if that's the case, you're going to consider 50 periods. So if this is the case, we can use the future value of 1. What is this? This is simply the formula 1 plus I raised to the power of positive n, where I is the interest rate per period and n is the number of periods. So what will you do with this future value factor? You are just going to multiply it with the investment and then you're gonna get the future value of the investment. Or stated differently, in order to get the future value of the investment times 1 plus I raised to the power of positive n, or future value of 1. So let's try it with the recent problem. We have 1 million times 1 plus 0.05 raised to the power of 5. You solve first the future value of 1. Then you should be getting 1.131408 and so on, because this has been rounded off. Then multiply it with the investment and then you're gonna get 1,131,408. As you have noticed, they have similar answer with the timeline method. So if you know the future value of 1, then it doesn't matter how many years is the maturity date for investments or debt, you can solve it easily. That is why this time value is sometimes called as the long cut and this one is the shortcut. So that's it for part 2 and part 3. The part 4 and part 5 is all about future value ordinary annuity and annuity due. So it will be better if we go directly to the illustration. So the problem is very much similar with the previous. However, instead of investing 1 million at one time, you decided to invest it in staggered basis of 200,000 every 6 months. So what will happen? On a timeline analysis, you will start investing at the end of 6 months. So if this is now, you're not going to invest here. You're gonna invest here, the 200,000, and then the 200,000 will grow times 1.025. It will become 205,000 at the end of year 1. So after that, you're going to invest the second 200,000, and then at the end of year 1, you have 405,000. The 405,000 will then grow again times 1.025. You have 415,125 plus the third 200,000 that you're gonna invest. You have 615,125. You multiply that again by 1.025. You're gonna get 630,503. The fourth investment of 200,000 will be added, and then you're gonna get 835,03. And lastly, in the last or the end of 2.5 years, the 835,03 times 1.025 will have 851,266 plus your last investment of 200,000, then you're gonna get 1,051,266. But then, if we are talking about long maturity periods again, it would be unwise to make a timeline analysis like this one. So we have the shortcut or the formula, which starts with the base formula. As we discussed earlier, that's 1 plus I raised to the power of positive n. But this time, you're gonna add two elements, which is the minus 1 and the divided by I. So that is what do we call as future value of 1 ordinary annuity. And what are we going to do with this future value factor? Of course, you multiply that with the investment per period. So let's have the proof. Let's substitute the elements of this formula with the given in the problem. So your investment is 200,000 times 1 plus 0.025 raised to the power of 5 minus 1 over 0.025. Now, if you solve this one, and if you're correct, you should be getting the 5.256328 and so on. And you're gonna multiply this one with 200,000. So your investment will become 1,051,266 at the end of 2.5 years using the shortcut or the formula. Now, the 1,051,266 is the same with the timeline analysis. How about the annuity due? So let's assume the problem above, except that the 200,000 is made at every beginning of the period. So now you're going to invest the 200,000 and then it will grow to 205,000, and then you add the second investment of 200,000, you have 405,000, and it will grow to 415,125 plus 200,000, you have 615,125 times 1.025, you will have 635,03 plus 200,000, you have 835,03, and then your last investment will happen at the end of year 2, but the 835,03 will grow to 851,266 plus your last investment, you will have 1,051,266. But then again, the question is after 2.5 years, so 1,051,266 will have the opportunity to grow, and it will grow up to 1,077,547. So these two are similar because you have 200,000 here as investment 5 times. However, they are different on the timing. The first investment here is due immediately. That's why the fifth investment happened at the end of year 2. How about here? The investment only started after 6 months. That's why the fifth investment of 200,000 happened at the end of 2.5 years. In the shortcut or the formula, you have investment per period times the base 1 plus I raised to the power of n. However, as you remembered, we added two elements for the ordinary annuity, the minus 1 and the over I. And since we are already here, we need to add two other elements, which is the plus 1 on the n and the final minus 1. So this is what do we call as future value of 1 annuity due. Now, to guide you, since the formula has been complicated already, so let's substitute the given in this formula. So you have 200,000 times 1 plus 0.025 raised to the power of 6. So as you can see, in the previous we used 5, but since we are already on the annuity due, you added 1, so that's why it's 6. So before you solve any others, you need to solve first the 1 plus 0.025 raised to the power of 6 before you deduct this one. Now, if you got the answer for this one, that's the time that you are going to deduct the 1. And then after you get the answer for this one, that's the time that you are going to divide the 0.025. And after you get the answer for this whole, that's the time that you are going to deduct the final 1. So, if you did that, you'll be able to get the 5.387736 and so on times the 200,000. You are going to get the same answer with what is your answer on the timeline analysis. So that's it for future value of 1, ordinary annuity, and annuity due. Let's have a little summary. So if the question is how much will be my investment after a period of time, then if that is only one-time investment, then you use investment times 1 plus I raised to the power of positive n, or what do we call as future value of 1. But if your investments are multiple uniform investments and it is contributed at the end of each year or each period, then you're gonna use investment per period times 1 plus I raised to the power of n. However, you're going to add two things. The first one is minus 1 over the I. And if it's still multiple uniform investments, however, it is contributed at the beginning of each period, then you use the investment per period times 1 plus I raised to the power of n minus 1 over I, but you're going to add another 2. You have plus 1 on the n and the final minus 1. So that's it for part 4 and part 5. Let's go now to the final topic, which is entitled multiple and equal investments, and let's go directly to the illustration. You want to invest 400,000 at the end of year 1, but only 300,000 at the end of year 2 and 200,000 at the end of year 3. The investment is to earn 7%. How much will it be after 4 years? So let's prepare a timeline for 4 years. In this particular problem, 4 years is equivalent also to 4 periods since there is no mention about quarterly, semi-annually, and etc. So now, at the end of year 1, you're gonna have to make an investment to 400,000, and then it will grow to 428,000, and then the second investment will be added. You will have 728,000 times 1.07. You're going to have 778,960 plus your last investment of 200,000. Then you will have 978,960. But since the question is how much will it be after 4 years, the 978,960 will be multiplied by 1.07. Then you're gonna have 1,047,487. How about the shortcut or the formula, sir? Unfortunately, there is no shortcut. Each of your investment payment, 400, 300, and 200, will be treated separately. So, the formula is investment times 1 plus I raised to the power of n in order to get the future value. So, let's start with the recent one. The recent or the latest payment that you're going to make is 200,000. It will be multiplied with 1 plus 0.07 raised to the power of positive 1, which will equal to 214,000. But we need to explain why is the n positive 1, sir? Because this 200,000, your last payment, has only 1 year of opportunity to grow. The next is 300,000 times 1 plus 0.07 raised to the power of positive 2. Why 2? Because it has 2 years to grow. So you will have 343,470. And of course, the last is 400,000. And you are going to multiply it with 1 plus 0.07 raised to the power of positive 3 because it has 3 years of opportunity to grow. And then you'll have 490,017. If you're going to add these 3, you're gonna get the same answer with what is on the time value. So that's it for all the parts. So we have already answered one particular question in this video, and that is how much will be the future value of the investment, where the rate and the amount of investment was given. In the next video, we are going to answer 2 questions. The first question is, if one wanted a specific value in the future and the rate of return is given, how much should one invest? For example, Mr. A wants to have 3 million in 3 years time to buy a car. If the rate of return is 10%, how much should A invest now or invest per period, meaning the desired future value is given, the 3 million. The rate of return is also given. What's missing is the investment or investment per period amount. The second question is, if one has available money to invest, how much should be the rate of investment to have a specific amount in the future? For example, Mr. A wants to have 3 million in 3 years to buy a car. Mr. A can invest 230,000 per quarter. What should be the rate of return of investment in order to reach the targeted 3 million after 3 years? So in the second question, the rate is the one missing. The investment amount is present as well as the desired future value is given. To get the missing rate, we need to discuss interpolation on the next video. So that's it for this particular video. You are welcome to play and replay this video until you are satisfied. If this helped, click like, subscribe, and share to other accounting students, and also please hit the notification bell to be updated on my next videos.